Thank you, Angus. Well, thanks for the nice introduction, and thanks to the University of Birmingham for hosting this, and thanks to all of you for showing up. There's 3 words up there in my title, and I'm not going to treat them in the order they're up there. They're up there just because that made it sound nicer. I'm going to start by telling you just a little bit about what we mean by randomness, what random phenomena are, how to think about randomness. I'm then going to tell you a little bit about deterministic phenomena, and we're going to look at the contrast between, is a random thing necessarily unpredictable? Is a deterministic thing necessarily predictable? You might think that they are. Hopefully by the end of the talk I will convince you that neither of those implications is true, and I'm going to do so via the medium of playing some games with symmetries. So let's make a start. Randomness. Let me tell you a bit about random phenomena. Well, I'll tell you about an evening I spent recently. My poor boyfriend and I spent an evening at home, nicely tucked up against the Scottish colds of St Andrews. What did we do for this evening? We threw dice. That's how much fun it is being the boyfriend of a mathematician. Well, we threw dice a lot and recorded what happened. And here's what we got. So, this is 600 dice throws, you can see charted up there. It took us a little bit of time. What do I want you to notice about those 600 dice throws? Well, I picked dice because they're probably the prime example you would all think of a random phenomena. When you throw the dice, you don't know what's going to happen. But what do we see over 600 throws? Well, actually, the number of times that each side has come up is roughly equal. I think the biggest number away from 100 there is 110, which is the number of times that 1 came up. The smallest number below is the number 4, which came up 93 times. And actually, number 5 came up exactly 100 times. So although something random is going on, you see what's called uniform behaviour. It's a uniform distribution in terms of how likely it is for each specific event to arise. Let's get personal. So I'm going to ask, I think probably the middle front block here. So everybody up to the cameras, down in the middle. A personal question. I'd like to know the last digit, if you wouldn't mind, of your mobile phone number. I'm not going to ask for the whole of your mobile phone number. That would create, I'm sure, all sorts of data protection issues. But I think you can probably tell me the last digit without revealing too much about yourself. I'm specifying mobile phone because I don't want you to have any choice as to what number you pick. If you don't have a mobile, your landline is fine. But if you do have a mobile, please give me the mobile number. And what I'm going to do is draw up a chart of your answers. So first of all, could everybody whose mobile phone number ends in a 1, who's sitting in this middle block, stick their hands up now, please? 1, 2, 3, 4, 5 of you. All right, my slightly wonky bar chart's now going to look like that. How about number 2? 1, 2, 3, 4. 4. Number 3? 1, 2, I think that's 3, 4 again, I think. Right, number 4. 1, 2, 3 of you. Okay, we seem to be getting less popular as we work our way down. Number 5. Oh, loads. 1, 2, 3, 4, 5, 6, 7. 6. 1, 2, 3, 4, 5. 7. 1, 2, 3, 4, 5, 6, 7, 8. 8. Very keen, excellent. That's 6 of you. 9. 1, 2, 3, 4, 5, 6, 7 again. And finally 0. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so what do we see? I think we partly see that people got a bit more confident about putting their hands up as I went through. But what we also see is that these numbers are reasonably evenly divided. The smallest I got there was 3. The biggest I got there was 8. There's a good reason to see why I didn't ask for the first digit of your mobile phone number, because everybody would have given me a 0. But going right down to the last digit, they all wind up being pretty much equally likely. So what's going on here? Well, both the dice throw and the mobile phone numbers are in some sense symmetric. A dice, you can imagine a single die. It's a cube. There's no reason for one side to land more likely than another. For the mobile phone numbers, I'm sure they don't use absolutely all digits, but by the time they're down to the last digit, they're pretty evenly using all of the numbers 0 through to 9. So because all of these possibilities are symmetric, what we expect is that we're going to find a roughly equal number of each. You don't expect to find exactly the same number of each, but as the number of trials increases, so this was 600 dice throws, so it came out pretty well, versus only about 50-odd people, so it's a bit wonky still. As the number of trials increases, the proportion goes closer and closer to being even. So that's our first example of randomness. Okay, not only did we throw dice and record the scores, we also kept track. We threw them in pairs, so it was 150 actual dice throws of 2 each. And here's the graph we got for that. Now that looks very, very different from what we had on the previous slide. This is still a random phenomena, still dice throws, but in recording what the 2 dice summed up to, I'm seeing a very different pattern. So what's going on here, well, some of you might be able to work out, if I want to throw a combined 7 with 2 dice, there's 6 ways of doing it. I could throw 1 plus 6, 2 plus 5, 3 plus 4, 4 plus 3, 5 plus 2, or 6 plus 1. So there's 7 ways of doing it. Conversely, if I'm going to try and throw a 2, I have to throw a double 1. But there's still a symmetry in this pattern, of course. What we're seeing is that 6 is roughly the same as 8, 5 is roughly the same as 9, all the way down to 2 is roughly the same as 12. So there's a symmetry either side of 7 as we move away from 7. Well, this is quite a famous random pattern, and the reason why I've got that rather silly title is that normal, is because if you carry on doing more and more and more trials, and in particular if you do something where you're going to measure something, famously in one instance chest circumferences of Scottish soldiers, you will indeed find that it forms this pattern known as the bell curve. Now, the mathematician to first really use this was a long time ago, 1801, 23-year-old Gauss, who was a famous mathematical prodigy. An astronomer called Piazzi in Italy had spotted what turned out in the end to be the asteroid Ceres. There was a great deal of excitement about this because they could tell that it was a big object. But he didn't get to see it for very long before it disappeared behind the sun. So they didn't have very many measurements. So a race went on all around Europe to try and predict, as best as anyone could, where Ceres was going to be when it reappeared from behind the glare of the sun. Various eminent mathematicians made predictions. The virtually unknown 23-year-old Gauss, well, he worked out that when you measure things, you make mistakes, of course, always, we all do. And that mistakes, unless there's some systematic reason for error, they'll follow a pattern like this. The most likely thing will be no mistake at all. A little bit of a mistake will be reasonably likely, but not as likely as none at all. And bigger mistakes will get rarer and rarer and rarer. And in particular, they're going to get symmetrically rarer and rarer and rarer. You're as likely to overestimate as you are to underestimate. So he was able to guess that the predictions they did have were likely to be wrong, but they would be wrong using this pattern. So he developed a statistical technique called the least squares rule, made a prediction for where Ceres was going to appear that was miles away from anybody else's, and lo and behold, when it came out from behind the sun, it was exactly where he'd said it was going to be. So that's what the normal distribution's about. So you might think, well, this is another kind of randomness, and again here, I can say with a bit more certainty that if I throw 2 dice, I'm going to get a 7, but I still can't say in any way for certain. There's more numbers up there that aren't 7s than there are 7s up there. All right. So we've got a most likely thing, no error, or the number 7, and other things become less likely in a symmetric fashion as we move away from 7. Well, let's think about determinism then. What do I mean by determinism? Well, I mean a situation where there's no chance involved at all. If I drop something, it's going to fall, and it will hit the first thing it can hit. If there is no chance involved at all, then we say that the situation is deterministic. Whoops. So determinism was a key concept, I guess, in physics ever since the Newtonian revolution. It was believed that if we could completely work out where everything in the universe is, then we will be able to say in future exactly where everything in the universe is ever going to be, ever. There's no actual chance involved. Okay, this function is pretty deterministic looking. what do? You pick a number x. You pick a number x between 0 and 1. And what the function tells you to do is multiply it by 4, and then multiply the answer by 1 minus itself. Okay? So if I was going to take the number 1 initially, well, 1 minus 1 is 0, so the overall thing would come out to be 0. If I was going to pick the number half initially, I'd do 4 times a half times 1 minus a half. So I've done 4 times a quarter, and I would get 1 back again. All right. I've only defined it between 0 and 1. It's a fairly easy exercise to show. If you substitute, any of you that are feeling keen, a half plus y in place of x, then you can easily convince yourself that if you plug in a number between 0 and 1, you're going to get a number between 0 and 1 out. No chance. Nothing very surprising. What we're going to do, though, is consider what happens when we apply this function repeatedly. So I'm going to put a number into f, get some output, put that output back into f, get some more output, keep cycling around and seeing what happens. So here's an example. I've started out with 0.1. So the first thing we're going to do is work out f of 0.1. So that's 4 times 0.1 times 0.9, and that's going to come out to be 0.36. I've not put all the values up there. Now what we're going to do is work out f of 0.36. So it'll be 4 times 0.36 times 1 minus 0.36, which I have a little crib sheet, tells me is 0.9216. Biggish. We're then going to put that back in, put those back in, and eventually we get a pattern of dots. Doesn't look like there's much to say about that pattern of dots. Pattern of dots. Anyway, that's what happens with 0.1. What's interesting is what happens if I pick a very, very similar number. I've changed it by 0.01. Rather than putting 0.1 in, I'm going to put 0.11. Let's see what happens when we repeat the experiment. Well, f of 0.11 is 4 times 0.11 times 0.89, and that comes out to be about 0.39. Previously, that was 0.36, so we're out by a little bit more. You can see when I apply it again that I'm differing by a little bit more again. When I push that number through f again, I'm now differing by really quite a lot. And if I keep pushing it through f, eventually I get about as far apart as it's possible to be while staying within the range 0 and 1. So I've changed my input by just a little bit, and after applying f 6 times, I've got an output that's pretty close to being the opposite end of the scale. Well, maybe I cheated here. Maybe differing by 0.01 is in some way significant. Let's try it again with a really, really close number. So this is now 0.101. I'm only differing now by 0.001. You can barely see the black dot behind the green one, right, when we start? You can see a tiny crescent of black behind the green one. Apply f again, and that crescent's getting a little bit bigger. We've now begun to separate. It's all seeming quite slow. But then what happens is suddenly everything accelerates, and by the time I'm on 10 iterations, I'm miles and miles and miles away again. Okay, so I only differed by 0.001, and at the end, after only 10 trials of running f, I'm miles away. What do we conclude from this? Well, this is a deterministic system. But suppose this was actually describing something physical. Suppose you actually had to take a measurement. If you're going to take a measurement, you're only going to be able to measure to a certain number of decimal places. You can't measure to infinite precision if it's something out there in the real world. So if your question is what happens after 100 time steps of me running f each time, the answer is you do not know. You cannot know if you're taking it from the real world. This is the very beginnings of an area of maths known as chaos theory, which was actually the best-known name associated with this is, in fact, a meteorologist, that, as Hillary's going to be talking about meteorology, named Lorentz. And he was running trials on the atmosphere on a computer, looking at how air circulated in the atmosphere. And because of his access to the computer, he was having to run the trials in batches. So he'd do a certain amount of computation and then stop and record where he'd got to, and then start again the next time he had some computer time with the data that he'd stored from the end of the last one. And then to check, he was running different batches. And he started getting completely and utterly different results. Now, all that was happening there was he had a function like this, but more complicated, and his computer was storing it internally to a bigger number of decimal places than he was storing it when he wrote it down to feed in again. which meant that if he was interested in long-range prediction, he works out you could say nothing. So this is called chaotic, and in answer to my question, are deterministic things predictable? Resoundingly not. All right, let's talk about symmetries. They're my real love. Symmetry. Well, I've used the word symmetry twice already in this talk. I used symmetry to describe a cube, but it's the same any way up. You can't tell the difference between it. And I also used symmetry to describe that chart of the scores of the dice. I said that it was symmetric as we got either side of 7 and moved away. In general, for this talk, a symmetry sounds like a slightly pointless thing, actually. It's a way of moving something around so that you can't tell you've done anything, right? You're going to do a whole load of stuff, and at the end, it's going to look exactly the same as if you'd done nothing at all. Let me give you some examples. This here is the London Math Society logo. It's a decagram. So this is a 10-pointed star. OK, well, you can see that if I rotate it around by 1 point, it's going to look the same as it did before. If I rotate it round by 2 points, it's going to look the same as it did before. If I rotate it round by any number of points, it's going to wind up looking as if I hadn't touched that picture. One thing I can't do with the star, that's another common symmetry, is I can't reflect it down any mirror lines. Because of the way that these lines are over and underlapping, if you tried to put a mirror anywhere down that star and see whether one side was the same as the other side using your mirror, you would find that they weren't. All the under and overs would be the wrong way around. So that star has some rotational symmetries, but it does not have any reflection symmetries. Here's another picture. So this is from the Alhambra Palace in southern Spain. Famous, beautiful palace. If you ever get a chance to go on holiday near Granada, I recommend that you go and visit it. And the whole of that palace is covered in beautiful tiling patterns. And what we've got here is a picture, I imagine, of some wall. Now, this is a maths talk, so I'm allowed to say stupid things. I want you to imagine that this wall is infinite. Okay? It's not, but for the purposes of the talk, it's infinite. If it was infinite, then there's some symmetries I can do here. In particular, if it's infinite, I can move all of the tiles 1 row up. Wouldn't work if it was finite, but assuming this wall goes on forever and the palace is infinitely big, then yes, I can move the tiles 1 row up. What I could also do is move the tiles 1 row sideways. So unlike here, where I couldn't do any kind of physical moving at all because I just had the 1 star, here I can bodily move the whole thing around as long as we're willing to imagine that it's infinite. There's also a whole bunch of rotation symmetries you can probably see. I can rotate through the middle of the big white squares. I can rotate through the middle of the small white squares. And slightly harder to see, but still there, is I can rotate through the green kind of lozenge shapes as well. And there's also a whole stack of reflection symmetries. So this is some notion of how many symmetries we've got. Let me tell you a few things about symmetries. There's one symmetry that everything has. This is a bit zen. Don't do anything at all. This is the symmetry that's kind of the sound of one hand clapping or whatever. You're just going to look at it and say, I'm going to do nothing. And you can do that to anything. And it's very, very important that we count that symmetry. I'll tell you why in a bit. So any shape you like. Everything is symmetric. This is not a very symmetric thing, having been crumpled. That's still got one symmetry. Anybody who's ever told you they're wearing an asymmetric haircut or an asymmetric skirt, they're wrong. It's got one symmetry, the symmetry that's doing nothing. Another property of symmetries, if we look back at my star, the LMS's star, I suppose, if I apply one symmetry, say I move it round 2 points, and then I apply another symmetry, I move it round another 3 points, say. So I've done one symmetry, I've done another. Well, the net result is going to be the same as having moved it round 5 points. So if I do one symmetry, then I do another symmetry, there's always some third symmetry that I could have done rather than doing 2 jobs. I could have just done 1 job. So, for example, with this one, if I was going to move them up 1 row, and then I was going to move them sideways 1 column, well, I could have just moved them diagonally 1. There's always another symmetry there. Wanting this to be true is one of the reasons why I want this to be true, because I want it to be the case that if I move it round 5 times, and then I move it round again 5 times, then I've got a symmetry. But the net result of that is I haven't moved it at all, because I moved it round all of its points. Sometimes, therefore, we can combine symmetries, do one and then do another one. Sometimes, therefore, one symmetry can be used to make all of the other ones. So with this star, if I pick the symmetry that's just move it around 1 point, and I allow myself to do that as many times as you like, I can eventually get that 1 point to every single point of the star. Conversely, with the tiles, it's a little bit harder to see, but because I've got infinitely many moves up the way, and I've also got infinitely many moves sideways, there isn't any one symmetry that's going to let me make all of the others. So sometimes one symmetry will make all the rest. Sometimes it won't. Okay. Here's our first classification of symmetries. I'm going to start then by analysing symmetries by showing you some pictures with really not very many symmetries at all. So I put arrows on this to make it have even fewer symmetries than it otherwise might, because I want you to imagine we're only allowed to preserve the direction of the arrows. So what can I do with that triangle? Well, I can move it around 1/3, I can move it around 2/3, or I can look at it and go, nah, not touching it. That's my do-nothing symmetry. So it's got 3 symmetries. And what you can see here is just like my 10-pointed star, one symmetry there can be used to make all the others. Okay, if I move it around 1/3 and do that again, then I moved it around 2/3, do it again, and I've done the do-nothing symmetry. So one symmetry will make all of the rest. And notice that it's a triangle and we've got 3, so that's kind of nice. Building up a bit, I'm sure I can go more quickly through this one. I've got a square. Well, what are the symmetries of that square? I've deliberately put some arrows on to kill a bunch of the symmetries, so all that's left is the move it round ones. I can move it round 90 degrees, 180 degrees, 270 degrees, or I can sit down and go, nah, not bothering. So that square there's got 4 symmetries. And again, moving it around 90 degrees will let me make all of the rest, as long as I'm allowing myself to do that more than once. And similarly, I'll come back to this in a minute, there's a hexagon, that's got 6 symmetries. Now, a key point of mathematics is, well, mathematics the way I do it, is we're often not very interested in the actual objects. We care a great deal about the symmetries. We don't care very much about the shapes that we're doing them to. We just care about what the symmetries look like. So here, for your delectation and delight, are 2 different rectangles I've drawn. You can probably see that one of them is somewhat longer than the other one. But these 2 rectangles, well, in both cases, what have they got? I can reflect them horizontally, I can reflect them vertically, or I can do a combination of a horizontal and vertical flip, which is the same as rotating them around by 180 degrees. Both of them have exactly the same set of symmetries. So as far as this talk's concerned, I don't want to worry about the difference between those 2 rectangles. Now, this is where the hexagon comes in. When I move around the hexagon, the key thing is just how many times I've moved it round. So if I just want to keep track of the symmetries, I might as well use this wheel here. That's going to do the counting for me and let me actually see what I've done. Whereas moving that hexagon round, it's a bit hard to tell whether I've moved it twice or 3 times because it just looks like a hexagon, doesn't it? So we'll take as a convention, red might mean don't move the hexagon at all. Red's the do-nothing shape. If I want to move the hexagon round one side, well, that's the same thing as advancing my pointer one thing round the circle. If I want to move the hexagon on another one, well, that's the same as having moved it round 2 sides to start with, so I'm now down at the yellow. Another one, well, that's got me right down to a 180-degree flip. So you wouldn't be able to see it on the hexagon, but here you can see that I'm thinking of myself as having moved the hexagon round by 180 degrees. Move it round 4 times, we're now 2/3 of the way round. 5 times, and then by the time I'm back to 6, I'm at the do-nothing symmetry again. So once I've moved the hexagon round 6 times, I'm back to doing nothing. Since I'm sure you're all getting the hang of it now, you will see immediately, I'm sure, why this object is a good way of counting the symmetries of a 7-sided shape, a heptagon. So what this 7-sided shape, I can do nothing. I can move it round 1 twist, and then if I keep moving it round 2, 3, 4, 5, and 6, then when I eventually have moved it round 7 times, I'm back to where I started, and even with the aid of my lovely spinny wheel, I can't now tell that I've done anything. It's the same thing as having done nothing. All right, well, those were reasonably straightforward. Let's try and do something a bit more complicated. This is the bit of the talk that's, well, the first bit of the talk that's likely to go wrong. I have a triangle for you, and I've labelled the corners of this triangle so that we can see what I've done. And I'm going to give you the mathematical names for the symmetries of this triangle. Now, some of the symmetries are meant to be mirror symmetries, and I can't actually stick a mirror down the middle of the triangle, so it's also labelled on the back. So if I turn it over, that's the same thing as having reflected it down the middle there, but I've got to turn it over because it's a bit hard otherwise. So I'll show you the names that we've got for these. And I'm going to give you the proper mathematical names because I think they're actually quite usefully descriptive. So let's have the way the grown-ups play. Well, my first symmetry, I've just got 1 and 2 in brackets. What that means is swap 1 and 2. All right? If you just see 1, 2 in brackets like that, it means put the 1 where the 2 was, put the 2 where the 1 was. It's obviously a symmetry of this triangle. It corresponds to having a mirror down that line there. In a similar vein, you'll be astonished to know that the symbol 1 and 3 together in brackets means swap 1 and 3. Send the 1 to where the 3 was, and send the 3 to where the 1 was. I'll do it again when I go back to where I've started. And 2 and 3 is my vertical mirror symmetry. That's swapping 2 and 3 down at the bottom there. That's not all the things I can do to this triangle, though. I can do the same things to the triangle that I had to my picture of a triangle up earlier, so let's see that. This one, 3 numbers in brackets now. What does that mean? It means take 1, send it to where 2 was. Simultaneously send 2 to where 3 was. And send 3 to where 1 is. I'll do that again. I'm going to send 1 to 2, 2 to 3, 3 to 1, 1 to 2, 2 to 3, 3 to 1. So I'm allowing myself to turn it round this way now. What I would also like to be able to do is turn it around the other way. So this way says send 1 to where 3 is, 3 to where 2 is, and 2 back to where 1 is. I'll wind up looking like that. If I apply it again, I'm going to wind up looking like that. OK, what's missing? I've only got 5 symmetries there. I've been insufficiently lazy is what's missing. I need to remember that there's a symmetry that just consists of going, it's my triangle. I'm not doing anything at all to it. All right, well, with this triangle, I've got both rotations and flips going on. So it's not possible to pick one symmetry to make all of the others. Let me show you that. Suppose I wanted to pick one of the flips, any of the first 3 flips. So suppose I pick, 1, 3, say. What happens when I flip 1 and 3 is I fix 2. I keep flipping 1 and 3 till the cows come home and 2's not going to move. And I know that there are symmetries of this triangle which are going to make me move the number 2. So 1, 3 is not going to work. Similarly, if I were to pick 1, 2, 3, my rotation, well, I can rotate as long as I like. And I'm not allowed to turn the triangle over. So I'm never going to be doing any reflection symmetry. So I'm just going to be rotating and rotating and rotating and rotating. And obviously, if I pick the do-nothing symmetry, well, I'm not getting anywhere. So it's not possible to pick 1, sorry. But we can pick 2. So you may have to concentrate for this. So I've got 1, 2, and 3 going around clockwise, right? With the 1 at the top, at least from your point of view. I'm claiming that if I pick the 1, 2 flip, or the 1, 2, 3 cycle, I can actually make all of the rest. So let's go through the list. Well, the 1, 2 flip, I've already given myself that, so I can certainly make that. What about 1 and 3? I want to get 1 down to there, and 3 up to there. Well, what I'm going to do is I'm first of all going to do my 1, 2, 3 rotation. I've sent 1 to where 2 was. I've sent 2 to where 3 was. I've sent 3 to where 1 was. And now I'm going to use my 1, 2 flip. And what have I done having done that? Well, 2's still in its right place, but 1 and 3 have swapped sides. So I've managed to make 1, 2, 3 by using only 1, 2 and 1, 2, 3. Similarly, started out in the right position, so I've got 1 at the top and the whole lot going around clockwise. I want to make the 2, 3 flip. What I'm going to do for that is flip 1 and 2, and then I'm going to apply my 1, 2, 3 rotation. And now I did have 2 in that corner and 3 in this corner, and they've swapped corners. The rest are now easier. 1, 2, 3, well, I had that as one of my initial ones, and 1, 3, 2 I can get just by applying 1, 2, 3 twice. So apply it once and apply it again. I've done the same thing as going backwards 1. Do nothing? Well, you can either think of yourself as doing nothing, or you can think of yourself as flipping 1, 2 twice, say, and that's the same thing as not doing anything. So picking 2 of them lets me make all the rest. This is a different kind of collection of symmetries. All right. Let's think, then, about how likely it is that symmetries make other ones. Let's try and introduce a mixture between randomness and symmetry. Let's think what happens when we pick random elements from the symmetry group. And we're going to play it with this 6-wheel, and we're going to play a game. And there's prizes for this game, so those people that sat near the front are in luck because they're in line to win prizes. OK, what we're going to do is I'm going to go up to them and offer them a choice from a bag. If they pick incorrectly, then I win and I get a prize. And if they pick correctly, then they win and they get a prize. Colva loses. So what they're going to do is they're going to pick a random symmetry from that set of 6. And to make this more feasible, I have tennis balls. So you can see that these tennis balls have got numbers on them. 0 is going to mean the red one. 0 means do nothing at all. Move round 0 points. 1 is going to be move round 1 step of that circle. 2 is 2 steps. And then 3, just to convince you I'm not cheating, 4 and 5. So what I'm going to ask them to do is pick a ball from this sack. And the rule of the game is, if using that many moves I can eventually get to all of the sectors of the circle, then I win. I've got everywhere. If they manage to pick a ball such that I can't get to all the sectors of the circle, then they win and they get a prize. So, I need a willing victim. What number do we have? 5. OK. So, I'm allowed to move 5, and I'm allowed to move 5 as many times as I like. So what happens here? 1, 2, 3, 4, 5. I've now got green. 1, 2, 3, 4, 5. I've got pink. This is boring. Going forwards 5 is the same as going back 1. So going back 1 will get me from pink to orange, orange to yellow, yellow to blue, blue to red, and now I've been to all of them, and I win, which means I get a big tick, and I also get some Haribo. All right. Let's try again. What are we going to get this time? Number 2. Number 2. The lady has picked the number 2. So what happens here? I'm allowed to move forward 2. I move forward 2, I go to yellow. I move forward 2, I go to pink. Got yellow and pink now. Move forward 2 again, got red, it's looking good, I got 3. I move forward 2 again, and I'm back to the yellow. And I keep trying, and I'm back to the pink. I keep trying again, and I'm back to the red. I have lost this game, and I have to give away some Haribo. All right, let's have a go a third time. Oh! There's always a problem when you're doing random things. They really might go wrong. So this time round, he's picked 1. This time round, I can go to blue, because that's moving forward 1. I can go to yellow, that's moving forward 2. I can go to orange, that's moving forward 3. On to pink, on to green, on to red, and lo and behold, I win again. All right, I was not expecting that. I am benefiting from Haribo bounty. Usually what happens with this game is I lose quite badly. So I'm just going to pretend that I'm a complete spoiled brat and that I want to win all the time rather than just some of the time. So what we're going to do now is rather than playing the 6 wheel, we're going to play the 7 wheel. I am introducing 1 extra ball, namely move forward 6 spots into this. Kai, your time is up. OK, gentleman in the front has picked number 2. Let's see what happens with the 7 and the number 2. If you remember, when 2 was picked for 6, that was the time I lost. So let's see what happens now when 2 is picked for 7. Come round 2, I get to green. Come round 2 again, I get to blue. 2 again gets me red. Then I get orange. Then I get yellow. Then I get pink. Then I get grey. I've won. All right, I think one more go. I'm slightly overwhelmed by Haribo at this point. Oh, president of mine, please choose a ball. Number 3. So, final game this, we're going to play with number 3. Okay, 1, 2, 3 gets me yellow, 1, 2, 3 gets me red, 1, 2, 3 gets me green, 1, 2, 3 gets me pink, orange, blue, and back to silver again. And it's clearly my lucky night, because yet again, Colva wins. We like this game. All right, I could play all night, but I'll probably die of overeating if we do. So let's move on a little bit and think what's happening here. With the 6 wheel, I wasn't expecting to be that lucky. With the 6 wheel, if people had picked the 0 ball, the stay at grey, then I couldn't have moved at all. So I would certainly have lost the game. If people had picked the 2 ball, which happened, or the 4 ball, well, I can only move an even number of steps if you pick 2 or 4. I can only move an even number of steps if you pick those, so I can't get to all the circuits of my circle. Similarly, if you pick the 3 ball, all I can do is come down to the bottom and up to the top again, and I'm going to do exceptionally badly. I only managed to get 2 colours if you pick the 3 ball. So the only ways that I could win, which is why I was a little surprised to win so often, was the 1 and the 5. The 1 means go forward 1, and the 5 means go back 1. The probability, therefore, that a random one makes the rest, well, there's 2 where I win. I win on the 1, and I win on the 5. So there's 2 possibilities out of the 6. That's 2 6, which we can cancel down to 1/3. How about the 7? Well, with the 7 one, the only one where I was going to lose, I was pretty confident on this 7 wheel, apart from identifying which one it was, is if you pick the 0 ball. The only way that I could lose is if I'm stuck at 0. If you pick any other number, by repeatedly working my way around, I'm going to make it everywhere else. So the probability that a random symmetry can be used to make all the rest is 6/7. 6 meaning move in some way, any way you like. Well, we can generalise. What's going on here? Well, what's going on with the 6 is that it's divisible by some numbers. It's divisible by 2, and it's divisible by 3. So if you pick a number that's a multiple of 2, well, I'm going to go round to 6 with multiples of 2, and then I get to 6, and that's the same as 0. And then I'm going to go round again on multiples of 2. So I'm never going to get an odd number, so I'll never make the rest. So you might have an inkling now of a theorem. If I pick a wheel with a prime number of elements, so that's a number like 7 that's only divisible by itself and 1, if I pick one of them, then a random symmetry makes the rest as long as you don't pick the do-nothing symmetry. If you pick any other symmetry, you're going to be able to make the rest. Well, that means, for example, if I were feeling exceptionally churlish with my Haribo, that if I picked, say, 101 wheel, then I would have 100 chances out of 101 of winning, and I would expect to win almost all the time. In general, we know, thanks to a certain Mr. Euclid, if he existed, and his school, if he did not, that there are infinitely many primes. The primes don't run out. They go on and on and on forever. So this means that you can make that probability as close to 1 as you like. Okay? You're only taking 1 away from the top of the fraction, and the bottom of the fraction is the whole prime. So what we're seeing here is something very random, choosing a ball out of a bag of tennis balls, where the event itself is random. You can't say anything much about what ball's going to come out, but you can say an awful lot about what's going to happen if you allow yourself to play that game repeatedly. Okay. What do we do with symmetries? We've seen some things about symmetries now, right? Some of them you can make a whole family with just 1. Some of them you need 2 to make a whole family. Sometimes they've got things inside them, sometimes they don't. Well, here's a man who spent quite a lot of time thinking about symmetries. This is Galois. He was interested in trying to find solutions to quintic equations. So this is any equation that looks something like x to the 5 plus, I don't know, 4x to the 4th plus 3x squared plus x plus 1 equals 0. Equations like that, where the first thing is x multiplied by itself, so you've got 5 copies of x. Now, it turns out, and this is something that I can't explain to you in this talk, that a really important way of thinking about equations is to think about the symmetries between the solutions of the equations. And that's what Galois did. And he was able to prove at the tender young age of 19 that there is no general formula for solving equations like this. So you probably know the solution to a quadratic equation. There's a nice formula for it. If any of you have had particularly sadistic teachers, you will know the solution to a cubic equation and possibly even a solution to a quadratic one. There's a nice formula you can use. He was able to prove that there is no such formula for the quintic. How did he do that? Well, he did that by thinking very deeply about symmetries. He was able to characterize the symmetries of the solutions to equations like this and prove that if they had certain properties, then the equation couldn't be solved using just things like multiplying 4 by 3 and then taking a square root and these kind of tricks like you've seen in the quadratic formula. You will notice that young Master Galois has rather short life dates. So he did all of this when he was rather young. And then he got involved in a duel over a lady and was shot in the stomach and died in the arms of his brother. His final recorded words to his brother were, "Don't cry, it needs all of my courage to die at 20. But before he was 20, he had revolutionised maths for the next 300 years. It took a little while before we all found out about this. I thought I'd put his picture up. So the next 3 slides are what he did, and he'd done a chunk of this when he was about 17. So all of you young'uns in the audience, you should be getting busy. What did he do? He started thinking about how to break up sets of symmetries. But before I can tell you too much about that, I'm going to have to give you just a small number of proper mathsy words for things. So rather than talking about sets of symmetries from this point, I'm going to use the word group. A set of symmetries of some object, the 6 symmetries of this 6 wheel, the 7 symmetries of the 7 wheel, those are groups of symmetries, all right? They form a group. So when people ask me what I do if they're a mathematician, I don't say that I study symmetry. I tell them that I'm a group theorist. I study the theory of groups. Most groups, Galois discovered, contain smaller groups. Let me give you an example inside here of a smaller group. We saw that if the 2 was picked in the tennis ball game, that I got stuck on these 3 points. So inside this set of 6 possible moves, there's a set of 3 possible moves. And the thing that makes those 3 a group in their own right is that property that I mentioned at the very beginning about symmetries. I can combine any 2 of them and get another one in the set. So if I pick move forward 2, and then I pick move forward 4, I get move forward none at all, the do nothing symmetry, which was one of the 3 that I started with. If I pick move forward 4, and then I pick move forward 4 again, say, I get move forward 2, which was one of the ones that I started with. Conversely, if I tried to make a group with just, say, the do nothing symmetry and the symmetry that was move forward 1, well, if I did 1 and then I did 1 again, then I've got move forward 2, and that wasn't one of the ones I picked in the first place, so that's not a group. To be a group, I have to be able to combine any 2 and get a third. Here's another smaller group of symmetries. So we saw the 6 symmetries of this. One of the smaller groups inside it is just all the rotations. If I do a rotation and then do another rotation, the net result is a rotation. Okay, so Galois worked out that these were important. And then he went further than that. So we've seen the 3-wheel. He defined a particularly important kind of smaller group of symmetries. You'll have to concentrate for just a minute. So, I've got some smaller group of symmetries in my head. Say the rotations. All right. What this tells me to do is to apply any symmetry from the bigger group. So let's try switching 1 and 2. All right, I've now switched 1 and 2. Now, let's apply any symmetry from the smaller group. So that means rotating. Rotate. We've rotated. I now have to undo the symmetry that I first thought of. Well, the symmetry that I first thought of was switch 1 and 2. So let's switch 1 and 2 again. What we find is the net result is a rotation. These numbers are back in clockwise position. I've done a mirror reflection, and then I've done another mirror reflection again. So the answer is guaranteed to be in the rotation smaller group of symmetries that I first thought of. So what I say then is that the smaller group of symmetries is normal in the bigger group. This is normal inside all of the symmetries of the triangle. Let me show you an example that's not normal. Suppose I just wanted to flip 1 and 2. That's a smaller group of symmetries, because if I flip 1 and 2, all I get is flip 1 and 2 and do nothing. OK, apply some symmetry from the big group. I'm going to send 1 to 2, 2 to 3, 3 to 1. Now I'm going to apply a symmetry from my smaller group. I'll flip 1 and 2. And now I need to undo what I first thought of. So that means sending... Hang on. That means sending 1 to 3, 2 to where 1 was, and 3 to where 2 was. Well, I've not just flipped 1 and 2, I've flipped 1 and 3. So I didn't wind up with just flipping 1 and 2. So some smaller groups are normal, and some of them aren't. Galois worked out that these were important. So why are they important? Well, he made this definition. If some group of symmetries contains, I've written non-trivial very small. I'll explain what I mean by non-trivial in a minute. But if it contains no smaller groups with that special property of being normal, where if you do something from the small one, undo what you first thought of, you wind up in the small one, then it's called a simple group. Simple groups are going to turn out to be really important. What's the non-trivial doing and why is it so small? Well, every group contains a smaller group that's just the do-nothing symmetry. If I just pick that, I can do that as many times as I like. I'm going to stay at the do-nothing symmetry. And obviously, if I do something, and then I do nothing, and then I undo what I first thought of, well, the net result is doing nothing. So that's always going to be there. We don't want to count that. That's trivial. So if we've got no non-trivial ones, then it's called a simple group. So here's a theorem, which Galois kind of managed to prove. If you take any finite group, you can actually break it up into simple groups. That's why these simple groups are so important. So think about, say, factorising numbers. You know that given any whole number, you can factorise it as a product of primes. Now, there's a couple of things that are true there. One is that you can always break it down into primes, and the other is that you might get the primes coming out in different orders. Well, in the same way, given any group, if it's not simple, I can break it up into simple groups. So this thing is not simple. It had a normal subgroup, which was the rotations. I can break it up into the rotations, and then when I do the division, it goes a bit funny, but what's left after division is just the idea of flipping. I'm not now saying anymore what the flip is, but I can flip. So similarly here, there's no guarantee exactly what order you'll find the simple groups when you do this dividing up, but you will break it down into these simple groups that can't be broken down any further, and you will always find the same number of simple groups of each sort. You've seen a family of simple groups already. These things may sound a bit abstract, but there's one up on the board. These p-wheels, if p is prime, we've already seen that if I pick any number and just keep applying that number, as long as it's not the do-nothing symmetry, I eventually make all of the rest. So they've got no smaller groups except for the trivial group, the do-nothing symmetry. So in particular, they've got no normal smaller groups inside them. Galois found another one. This object, that's a dodecahedron, has 60 rotational symmetries. I'm not going to work my way through all of them, but there's 60 symmetries of that. It's the smallest in an infinite family of simple groups. Those simple groups are called the alternating group. So this is called the alternating group on 5 points, the 60 rotational symmetries of this. And what Galois discovered is that there's a deep connection between the dodecahedron and his quintic equations. So let me finish by telling you a little bit about what mathematicians do with finite groups. We classify them. We want to know what all the groups are. We know that groups can be broken up into simple groups. So what we need to do is find what all the simple groups are. Amazingly, this was doable. Absolutely astonishing. The theorem says that there's 3 infinite families of finite simple groups, just 3, and then 26 leftovers. Just 26 groups that don't fit into any infinite family. It's amazing that the universe was this well behaved. The biggest of these 26 leftovers that don't fit into the infinite families is really, 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 really big. It's called the monster, and it's amazing that we can get our hands on something this big. It's got that many symmetries. That's quite a big number, right? It's about 10 to the 54. Consulting Wikipedia, you will find that that's approximately the number of kilograms of matter in the visible universe. So, 1 symmetry for every kilo of matter. How do you prove this? Well, Takes a long time. I wanted to mention this, at least partly because people here in Birmingham were involved in this proof, but also because you may believe that mathematics is done by people on their own in a room. This was a massive collaborative effort to prove this theorem. Hundreds of people were involved writing these thousands of pages. Maths really can be something you do with your mates over coffee or over beer. Once you've got this theorem, coming back to my randomness, it's quite easy to prove this theorem. That if I pick any of these finite simple groups from the infinite families or the leftovers, then I can choose two symmetries and combine them to make all of the rest. Even the monster, even all of those 10 to the 54 symmetries can be made by taking just two and combining them together. All right, let me draw this all to a close then by talking about random symmetries of finite simple groups. Back to tennis ball game. So Martin Liebeck and Anna Shalev were able to say that if you play the tennis ball game with bigger and bigger simple groups, then the probability that I would win if I kept picking bigger and bigger simple groups gets closer and closer to 1. No matter what odds you wanted me to give you for the tennis ball game, I could find a group that's big enough that I would definitely win if we played the tennis ball game with that group. This is a beautiful theorem. Unfortunately for me, I do computational group theory, and what it's not is having actual numbers. So here's my PhD student, Nina Menezes. This year, we needed to turn this theorem into numbers. This hasn't got any numbers in it. I want to write algorithms. I need numbers. We were able to prove that the simple group with the lowest probability of generating it, so if I pick just two and then I want to make all of the other symmetries, is the alternating group A6. So that's the next one up from the dodecahedron. If you pick any two random symmetries from that, then the chance that you can make all of the rest is 53/90. If you pick any other finite simple group, so if you pick a p-wheel for a massive prime, or if you pick the monster, then the probability winds up an awful lot bigger. If I could turn each kilo of visible matter in the universe into a tennis ball and play the monster game with you with the tennis balls, I would win more than 0.99999 times out of 1. All right, let me just conclude then. I hope that I've convinced you that sometimes, like with our chaotic function, behaviour can look extremely random, even when there's no randomness involved at all. Our little function, 4 times x times 1 minus x. Conversely, if we play the tennis ball game with the monster, doing random things, you don't know what symmetries you'll get out from the monster, but you do know that almost certainly I will win. Thank you.
So as you move up through these alternating groups and get to larger and larger groups, how quickly do the probabilities approach 1?
Really quite quickly. You get to better than 0.9 by the time you're at the 8th or the 9th or something like that. And then it kind of tails off a bit. But yeah, it goes pretty quickly. I mean, the way that this conjecture was first made was somebody looked at all of the simple groups of order less than 1 million and found that A6 was a complete outlier and everything else was very, very close to 1, and so conjectured that A6 was going to be the worst one of all. Yeah.